A very good morning. A very good morning to all of you. I hope you can hear me clearly and see my screen too. So let's start with today's work. Remember in last week's lectures we took an overview of Newton's laws of motion. In today's lecture and a few lectures from today we will take an overview of work energy. This week we plan to discuss the problems relating to work, energy, momentum, conservation of momentum, etc. So we plan to do that. Let me very briefly discuss the basic concepts involved in the work and energy that you have already done covered in your lower class. So we all know that work is has a particular definition in physics. So it's a scalar quantity. So I may write W is equal to, you integrate F vector F dot displacement. So it's a dot product of F and dx. The integration can be carried out to from some initial position x1 to some final position x2. If the force is constant, then you know that the F will come out and it will be just integration of dx. Also remember that we use the dot product that takes care of component of the displacement in the direction of force. Simple thumb rules: if the force and displacement are in the same direction, then the work is positive. Force and displacement being in opposite direction, work is negative. Now whenever the work is done on a body, we can always write down a work kinetic energy theorem. What is work kinetic energy theorem? That says that the total work done by different sources on a body, or I'll simply write WT, has to be equal to final kinetic energy minus initial kinetic energy. So you have to be careful here that this is written as the change in the kinetic energy, or sometimes I will simply write as delta K. So when you say total work, then the total work is absolutely the total work. I'm coming to it in a few seconds. So total work done is final kinetic energy minus initial kinetic energy. Examples are plenty. So for example, if you push a car, its kinetic energy increases from the rest, and if it's already moving car and if you apply brakes, then the kinetic energy decreases. So in both cases, in pushing and applying the brakes, you do work, kinetic energy changes. So these are the basic ideas of work and kinetic energy. Now what is W total? So the work done can be by various sources. It typically work can be done by conservative forces. So that can come in the category of work WC, the work done by conservative forces. Work can also be done by dissipative forces like friction, air resistance, etc. So W total will be given by WC, W work done by conservative forces, plus WD, the work done by dissipative forces. So both the type of force will do some work, and WT, when you calculate, you have to ensure that you have involved the work done by all the possible sources. Now, we also know that the conservative work done or conservative forces, or the the two examples of conservative forces that we can take are gravity and elastic or a spring forces. So Wg is given by mg force, gravitational force as we all know is mg, and displacement in the vertical plane, so I may call it y, so it may be mgy. It depends on plus or minus, depends on the movement of the body. If the body moves up, the work done by gravity is negative because the force and displacement are in opposite direction. If the body moves down, then the work done by gravity is positive because force and displacement are in the same direction. So that is the work done by gravity. The other example of conservative forces, work done by an elastic spring. So I will simply write as WEL is if it's a spring which is elastic spring which is following Hooke's law, then it is half kx square. So these are the two examples that you have studied. Most of your conservative work done examples will hover around these two examples, these two types. We can take it forward, and if you're attending this lecture, as I said, sit for all the lectures with pen and paper. You can write down along with me these points so that when we solve the problems, you have an access to them and you can always go back. We also know that the conservative forces are, uh, we also know that for work done by conservative forces, we can always define something called as potential, and I can always write the work done by conservative forces is negative change in the potential. So potential term can be defined. I would call potential energy as U. Change in the potential energy or negative of the change in the potential energy is work done by conservative forces. Remember, this applies only for the conservative forces. For dissipative forces, you cannot apply the concept of potential energy. So that that will that helps us to understand the conservation of total energy in in the presence of conservative forces alone. If only the conservative forces are there, then the total energy is also or always conserved. So that is written in many forms. One of the forms that I will write is this, that delta U, change in the potential energy plus change in the kinetic energy, if only conservative forces are working, is equal to 0. So if anytime potential energy increases, kinetic energy has to decrease, and vice versa. I can also write Oh, Hetanshu, thank you for pointing it out, my dear. Yeah, I mean, sometimes it can go wrong. You may send a long, I may send a wrong link. Let me see what link I did send. Oh, that is something else. Yeah, sorry for that. And I was just waiting here and wondering where are people. Okay, so I will just quickly take a pause since Hetanshu, you have pointed it out. I will quickly take a pause and just go through it, what we have discussed so far. What we have discussed so far is very straightforward. I defined the work as we have defined earlier, F dot dx, and I have discussed work kinetic energy theorem. This part is work kinetic energy theorem. So I can put it in a block. This is one set of definitions which says that the total work done is final kinetic energy minus initial kinetic energy, which is equal to change in the kinetic energy delta K. When you say total work done, it involves the work done by conservative forces plus work done by dissipative forces, both the types of forces. Two examples of work done by conservative forces we are already familiar, and they are work done by gravity and work done by elastic forces, WL. Work done by conservative forces is minus delta U. We can always define a potential energy function, and that potential energy function is the U, and work done by conservative forces can always be defined as minus delta U in both the cases, in case of gravity, in case of elastic. And then this gives me the law of conservation of mechanical energy. So this is the third law which I am writing, that the total change in the mechanical energy is always constant. Uh, but remember, this is only for conservative forces. So I will write just not full. So yeah, thank you once again, Hitanshu. Let's go ahead. So which this can also be written as the total kinetic energy or total final potential energy plus total or final, if there are more than one element in the system, then it's the total kinetic energy final, when I use the word 2, has to be equal to total initial potential energy u1 plus total initial kinetic energy K1, total initial K1. So final, this is total mechanical energy final. This is total mechanical energy initial. So total final mechanical energy, I will represented by E2, has to be equal to total initial mechanical energy. I will call it as E1, and that has to be constant. So that is a very important law that we have studied. Yeah. So another important thing that you have studied in these, when you covered these topics, was that the forces were derivable from a potential. So if you have a force F, then the force F is simply derived from a potential. So you use your del vector, operate it on the potential energy, and you get your famous equation that helps you to get the force from the potential energy. So you know how to expand this. This operator, del operator has three components: deva by deva x I cap, deva by deva y j cap, deva by deva z k cap. And the way we define everything, you can say that the force is negative gradient of potential. So the force always works in the direction in which the potential is dropping. Okay. Now, this is all about conservative. What happens if there are non-conservative forces also working? So if there are non-conservative forces also working, then the work done by non-conservative or dissipative forces, WD, also comes in the picture, and that will not make your uh, mechanical energy or the total mechanical energy remain constant. Your total mechanical energy will either increase or decrease. So for example, one of the classic example is throwing a ball up. So in your hand, if you have a ball and if you throw up, as your hand moves up, the speed of the ball increases, the potential energy also increases. Now, according to this logic, if only conservative forces had been working, an increase in the potential energy must be accompanied by a drop in the kinetic energy. But as you move the ball up in your hand, when the ball is in your hand, when its potential energy increases, its kinetic energy also increases. And that happens because there are other forces, not necessarily dissipative, but there are other forces working, doing work. So if there are other forces also doing work, then work done by conservative forces plus work done by other forces, which may be dissipative, non-dissipative, etc. I will simply write O. Total work done will lead to the change in the total mechanical energy. So the total mechanical energy is going to change if both of them are doing work. So we will see some of the examples. I will present these concepts, and then rest you can practice on your own. So let me take at least some examples. I have one example over here, which is, let me first read it for you, then I can make it little smaller and we can solve it on the same screen. Consider a hanging spring of negligible mass that does not obey Hooke's law. So the spring does not obey Hooke's law. When the spring is extended by a distance x, the force extended by the spring has a magnitude alpha x square. So you can see that the force is not proportional to x, it is proportional to x square. Alpha is a positive constant. The spring is not extended when the block of mass m is attached to it. So you attach a block of mass, then the block is released, stretching the spring as it falls. So there is a figure, we will draw a rough figure. How fast is the block moving when it has fallen a distance x1? At what rate does the spring do work on the block at this point? Find the maximum distance x2 that the spring stretches. Will the block remain at the point found in the part C? So we have a system where a hanging spring is given. So I can draw some simple sketches. Remember, sketches are very important in your problem practice. All you need to do is draw some rough sketches. You need not be very artistic, because what happens is when you draw a rough sketch, it improves your imagination or visualization of the problem. So I have this one, and the spring obeys a law which is, I would write here, F is equal to alpha, it's not K, some constant alpha x square. Now let us fix our coordinate axis. This is mass M which is attached. So I would like to take this point as the origin where the mass is attached and it is still not extended. So it's very important for us to figure out our frame of reference. Let me set my x-axis. Obviously my y-axis is vertical. I will take the point mass. What do I do? So I'm finding this medium fairly interesting. I can draw big drops, big circles here. So this is my point mass M, and my forces can work in different directions. What are the free body diagram? How would the free body diagram look like? So you can say that the free body diagram mg will work downward. So let us draw mg. Wait a minute. So let us draw mg in the downward direction. So this is my mg working in the downward direction. Spring force will definitely, as we all know, spring will stretch downward. So the spring force will work in the upward direction. What else? Is there any other force that will work here? So you can see that there is no other force. It has negligible mass. So now what else we can write here? I can mark the positions x1. So it is moving. So this has to be my x-axis, and horizontal will be my y-axis. So let me mark the positions now. So my positions are very straightforward. If I take this as this point, I may take as x1, and it has to go to some point x2, the maximum distance. So I may take it further down some point on the x-axis as my x2. Yeah. So how can I use the concepts that we have learned just now to solve this problem? You can try it. I can give you a minute to start working on this problem. Remember, you cannot use Newton's laws. Don't use Newton's law. Don't make a sum of the two and figure out your acceleration, and then from acceleration you go on to calculate other stuff. That is doable. We are not intending that. The work energy configuration is a complete alternative to Newton's laws, and they help us in many ways. In Newton's laws, it's a vectorial configuration. Work kinetic energy is a scalar configuration. Calculations becomes much easier. Also, if you remember, the whole idea of your Lagrangian mechanics evolve from what we are learning here. The work kinetic energy principles led to what is called D'Alembert's principle of virtual work, which in turn goes into Lagrangian mechanics and eventually the Hamiltonian theory. So this is very important for us. So F is equal to alpha x square. We can see that there are two forces working as this is going to descend in the downward direction. Let's say that it descends by an arbitrary distance x. I remember x1 and x2 are the specific distances. I take an arbitrary distance x to solve my problem. So work done by the elastic forces as it descends by an arbitrary distance x can be determined. So the work done by elastic or spring, as we all know, is integral of f dx. Remember, I took the starting point as origin. So start with 0, ends at x. I can easily solve this integral. This is straightforward. Why is it straightforward? Look at it. It is alpha x square. So alpha goes out. Alpha goes out of the integral. X square dx is x cube by 3. You put the higher limit, it will remain x cube by 3. If you put the lower limit, that will be 0, so gone. So it will be alpha x cube by 3. So this becomes my equation. Is it a correct equation? Is it incorrect equation? Can anyone tell me? Let me see if you are observant enough. If you can find the mistake in this, please write it to me. And in the meantime, I will write the work by gravity. Work done by gravity, I will take Wg. So the block of the mass is m and weight is mg, and the block has descended by a distance x as I have assumed. So the displacement is x. So the work done by gravity is mgx. Yeah. Now, has anyone found the mistake in these equations? And then obviously we will think about this again. If you have, then please tell me. In the meantime, you can notice that this formula is not half kx square because the spring does not obey Hooke's law. So if you get half kx square, it is possible only if the spring obeys Hooke's law. But nobody is writing to me what mistake could be here. So if you observe it carefully, you can see that the displacement will happen in the downward direction while the force is working in the upward direction. Since the force and displacement are opposite to each other, the work done will be considered as negative. So a minus sign has to appear here. Do remember that. What about the directions here? Let us check once again. So here mg is working downward, x is also going downward, so mgx is in the downward direction. So here the directions are correct. Here this correction is needed. Is there any other thing which is doing work on the block M? Answer is no. There is no dissipative, there is no touching it by hand, there is no air resistance, etc. So the rest is W others is 0. So I may write, if to be specific, you need not. Work done by other is 0. So the total work done, you can apply work kinetic energy theorem. So the work done total is equal to work done by, yes Bijin, you have found it finally. Work done by elastic forces plus work done by gravitational forces plus work done by, and that has to be equal to kinetic energy final minus kinetic energy initial, which is zero. System was at rest. So kinetic energy final is nothing but half mv square. Kinetic and your initial systems are mgx minus alpha x cube by 3. Now you have been asked to find out the velocity at x1. So you can see now that's a very straightforward thing. You put x1 here, you put x1 here, you calculate it for velocity. So if you do that, you will get it very easily. Your v is equal to, what do I write? So this is as it is, mgx minus alpha x cube 3 multiplied by 2, and this mass will go down, m and square root, so a square, remember this is x1, this is x1. So that gives me my velocity. Find the maximum distance x2 that the spring stretches. So what happens at maximum distance? Think about it. If you observe, think carefully, when it goes at the maximum distance, the spring stretches fully. And if that happens, the block will come to rest. The kinetic energy will become zero. Once the kinetic energy becomes zero, that means your initial is zero and final is zero when the system is fully stretched. So this side becomes 0, but this has become x2. So this will become mg x2 is equal to alpha x2 cube divided by 3. So 1 x2 will cancel, leaving a square here. Find x2. So you have to find x2. So it will become 3 mg divided by alpha and x2, so this will go under square root, and that has to be equal to x2. So that's my x2. Will the block remain at the point found in the path C? So that I leave for you people to explore. Will the block remain at the point found in part C, that is at x2? Think about it. You just have to figure out whether it is in equilibrium or not. If it is in equilibrium, then it will remain at its point. If it's not in equilibrium, then it will not remain at its point. How do you check whether the block is in equilibrium or not? Very straightforward. You find out the total force, upward, downward. If the total forces are equal to 0, it is in equilibrium. If the total forces are not 0, it's not, or they are not in equilibrium. Okay, let's take one more example. This is not so exhaustive. So a wooden rod of negligible mass of and length 80 centimeter is pivoted about a horizontal axis through its center. So as I said, I always prefer to draw a rough diagram. So I will draw a rough diagram here. We have a wooden rod. So this is the rod. The rod is pivoted about center. So about this point there is a pivot. A white rat. So there is a rat cling to one end of the stick. So I have a rat here. How to draw a rat? I have no idea. But maybe I can do some. And it has a tail. And the mouse with 0.2 kg. So can anyone tell me the difference between the rat and the mouse? I may draw them slightly different tails and different shapes. Assuming that they are at the end. Okay, their mass is given 0.5, 0.2. The mouse looks lighter in weight than the rat. That's one difference. System is released from the rest with the rod horizontal. If the animal can manage to hold on, what are their speeds as the rod swings through the vertical position? So the rod is pivoted here. So it is going to turn this way, and this is going to turn in this direction. That when they are vertical, that is at this position and at this position, what is going to be the speed? So this is a, if you read the problem carefully, you will find that the potential energies are changing. The heights of the two are changing. This is going up and this is going down. So I want you to think about it. Potential energies are changing. Kinetic energy is also changing. Initially at rest, kinetic energy is 0. As this goes up and rotates, the kinetic energy is increasing. Remember that the rod has a negligible mass. So the rod, if a part of a system has negligible mass, then its kinetic energy becomes negligible, because kinetic energy is half mv square. So even though it has speed, if mass is negligible, the kinetic energy does become negligible. So you can ignore the kinetic energy of the rod. You have to just focus on the kinetic energy of the rat and the mouse. But the kinetic energies of the rat and the mouse, if you observe carefully, do they have different velocities or do they have same velocities? So now, as problem says that they are cling to the rod, since they are cling to the rod, it's a rigid rod, wooden rod. Each part, I mean, will they have same or different velocity? Remember, the entire rod will have same angular velocity. That is definite. Linear velocity of the two particles will depend on how far they are from the origin. Now in this case, fortunately, they have the same distance. This is the center. Total rod is 80. So this is 40 and this is also 40. So both are 40. So we know that their velocities will be same. If this one is moving with the velocity v, then even That's right. Perfect, Deepanshu. This will also give the velocity v. So that is an important observation, Deepanshu. Once you have observed that their velocities are same, you have solved the problem. So you can apply the change in potential energy delta U of the system plus change in the kinetic energy delta K of the system has to be equal to 0. Let's quickly solve this. Now as this goes up, this will gain in the potential energy. By how much? So it's mg h, its mass is zero point 0.5. So I'm not writing those extra zeros. So zero point 0.5 into G, which is 10, I can take. I will simply write it as 5.5 into 10 into H. H is 40 centimeter or zero point 0.4 meter. So this is the gain in the potential energy, but this is going down. Remember, I'm taking 0 of potential energy at the center. This is very important. 0 of the potential energy reference is center. So this is going down. So this one is losing potential energy, and its potential energy loss will be minus mgh. So minus is, yes, Vinod. Minus is m is zero point 0.2, g is 10, so it will become 2, 2 into zero point 0.4, 2 into 0 0.4. Now, what is the change in the kinetic energy? Plus, so remember the initial kinetic energy is 0, it's only the final kinetic energy. The final kinetic energy of this is half m. M is zero point 0.5, so I will write point 0.3 into point 0.4. Yeah, okay, fine. 5 minus 2, that's right. I'm writing potential energy term. Potential energy term is straightforward, uh, into zero point 0.5 into V square plus there's potential kinetic energy of the this side. Again, it's 1 by 2 into zero point 0.2 into V square, and that has to be equal to 0. So once you solve this, now you can see that the only unknown here is V square. So you can solve this for V, and that will give you the final answer, because that's the speed which has been asked. So we will take more problems on work, energy, etc. in the next class. Thank you. I will start the Google Meet in 1 minute from now.